All right, last meeting. So I told you we were going to see some application of what we have seen, particularly Euler's second law. And the things that I'll be talking about are just scratching the surface of spacecraft attitude dynamics, of course. But you can find a lot more in this book if you're interested. The Space Vehicle Dynamics and Control. This is a must-have in your library if you're doing space work from Bongui. And it's an IIAA book. So I think there was a little bit of confusion about what we're trying to do. We're trying to look at what we can do to stabilize the orientation of a spacecraft, which is treated as a rigid body. And I told you last time, imagine you have some inertial reference frame and a coordinate system which is fixed in it, of course. And this could be just a generic inertial reference frame. So let's call this N. This can be centered at the Earth, so you could actually have the globe around this point O. The orientation of the axis, of course, does not rotate with the Earth because the center is already accelerating, so it's not properly an inertial reference frame. But in some instances, we assume it is good enough, and we said in this case we'll call it ECI, Earth-centered inertial reference frame. But you can also completely forget about this. This could just be centered at another planet. It can be centered at the sun. It can be centered nowhere, just a point in deep space. I don't really care about that. I just care about the fact that there is an inertial reference frame and some coordinate system attached to it. And then I have a spacecraft, and without loss of generality, I just draw it this way. It doesn't have to be this shape, of course, which I may want to point, for example, with one face. As we said, let's say that we have a sensor here, a camera, a telescope, whatever that is. We want to point this face of the spacecraft maybe always in the EY inertial direction. You may be looking at what's going on here with stars or another kind of experiment. And so if I also call these body axis EY, EX, EZ, again, without loss of generality, our goal is to point EY, little EY, in the direction of big EY at all times. It could be one requirement of your mission. And you don't really care about what happens, in principle, to EX and EZ, the little EX and little EZ. They can rotate as long as EY is pointing this way. And so I claimed last time that one way, of course, to do this is have thrusters on your spacecraft. You can have momentum exchange devices. I don't know which classes you've taken about these topics, but you can have reaction wheels and other things that spin inside your spacecraft. And you can spin them up or down and obtain changes in orientation. So you can have active control. Okay. But another way is also actually injecting the spacecraft into its orbit or on its trajectory, whatever there is, so that it's spinning about the axis at very high RPM, about the axis which you want to stabilize, because I want to point this axis to be fixed as much as possible with respect to inertial reference frame. And we'll show why there is a way to do it. And so last time I said, okay, if I put my spacecraft, this rigid body, let's call it R, right? If I put it in spin about this axis with an angular velocity omega r n, which is equal to, in the body axis, 0, some omega 2 or omega y, let's call it omega y, right, to be consistent, 0, and this is projected again in the body axis. I told you last time that if you can obtain that somehow, of course there will be some action at the beginning that puts your spacecraft into this state. But if you can reach this state, I told you that you are stabilizing this direction. So you're basically spinning about this axis only. These other two are going around. I don't care. The EY will always be aligned with big EY. And let's see these from a point of view of Euler angles. So Euler angles, remember, go back to the lecture, go back to the book. We define them for the sequence 3 to 1. I believe that's what we've seen. And then you had another question on your test on 1 to 1, I believe. The Euler angles are just a way to tell me how this coordinate system, the little e's, is oriented with respect to the big e's, right? Correct? So if I'm doing a 3, 2, 1 rotation, this means that I'm looking at EX here, EY here, EZ is here. And I, with the 3, 2, 1, I start doing a rotation. Let's see how I call them. I think I call these psi angle. And I create this intermediate axis here. And then I do a rotation about the second intermediate axis. And the angle is theta. And this generates other intermediate axis. This one is going below the plane EX, EY. And then my last rotation is about this final axis here. I'm sorry, 3, 2, 1, this down here, of an angle phi. And so this final axis here will be your little EX. And then you have here your little EZ, right? And here you will have your little EY. And I know that it's hard to visualize it here, but you have much better tools online, and you can have colors, and you have your book. But that's what happens. First rotation, psi generates, moves big EX, big EY to some intermediate axis here, which I think we called P when we did other angles, PX, PY. Then about this PY, you do a rotation theta. That moves EZ to this intermediate axis and brings your intermediate x-axis down here to be the final x-axis of the body. And then your final rotation phi moves your intermediate z and intermediate y into the final EZ and EY, right? It's just a way to tell how this body is oriented with respect to this coordinate system, because the little e's are attached to the body. And so I'm claiming that if I use, for example, a sequence of Euler angles 3, 2, 1, and that's my angular velocity, I know that that's the case, I am basically keeping this little EY always pointed in that direction. Which, in other words, looking at these angles, it means that I only see a variation in theta with time. It increases or decreases, depending on the sign. But the other two angles, psi and phi, are not going to change, right? So, well, let's do it quickly here. I brought with me the expressions that give me, for a 3, 2, 1, with a 3, 2, 1 Euler angles sequence. One of those things that I refuse to remember, you should do the same, because you can always derive them or look them up in books. This is what you get for your angles derivatives. They're equal to a matrix 0, 0, 1, sine of phi, cosine of phi, cosine of phi, minus sine of phi, and then I have sine of phi, sine of theta, cos phi, sine theta. This whole thing is actually divided by cosine of theta. Remember, that kind of sequence, second rotation goes to 90 degrees. You have singularity, which also mathematically shows as dividing by 0. So it all makes sense. And this is multiplied times the omega x, y, z, right? That's what I call them, x, y, z. OK, so with this equation, you just plug in what I'm telling you and assume that at initial time, we can always make that assumption, at t equals 0, your angles are 0, right? So at initial time, you are oriented as the inertial coordinate system. I can always change the body axis to something that is convenient to me. So start plugging in the numbers. Everything is 0 in here, these angles. So I have psi dot, theta dot, phi dot. That is going to be equal to, I see 0, 0, 1, 0, 1, 0, 1, 0, 0, times, I told you that that's the omega, so I actually have 0, omega y, whatever that is, 0. And that's usually set to be a constant. And so my differential equations for the angles are psi dot equals 0, theta dot equals this omega y, and phi dot equals 0. So if I'm able to maintain this condition and I start from an inertial orientation, psi dot is not going to change, phi dot is not going to change. The only one that changes is theta, which is the angle about the axis of spin. So this is just to show you, okay, if you put your spacecraft spinning about one of the body axes, which we're going to assume is also a principal axis of inertia, of course, for convenience purposes, it will keep spinning about that. It's a simple rotation about one axis. But this way we have demonstrated that that's true in general in 3D. Okay, so I want to study the stability now of that motion, because the idea of putting something spinning about an axis in space is so that that sensor is pointing always in the same direction. So if there are small perturbations, I don't know, a small meteorite hits your spacecraft, or something is not completely balanced in your spacecraft itself, something can always happen. You want to see if the natural dynamics tends to remain close to your spin condition. So I'm going to now imagine that I am actually around the planet, just for fun. So my satellite is flying on its orbit here. And as I said, I want to stabilize this direction, the EY direction. So I'm going to spin it about this axis. OK. And I'm caring here about the attitude motion, the orientation part of this rigid body. I don't really care if this rigid body is going around the planet, if it's flying away to the sun, whatever. I don't care about the trajectory of the center of mass. Why? Well, because that's the orientation part that I'm focusing on. And also because the equation of motion for this object, second Euler's law, tell me that ddt in, sorry, I call this n, right? In n of h bar in n is equal to m bar. This is the moment of all forces with respect to the center of mass. Unless this object is very big, the International Space Station, the center of mass and center of gravity are more or less the same point. So if you're orbiting around a planet or the sun, or you're going in interstellar travel, you can say that all the gravitational forces are more or less applied, so Fg, to the center of mass. So in other words, this is 0. Unless I have some active control thrusters, etc. But I don't want to study that problem. I want to study the free dynamics problem to see if this object, once it's put into spin, tends to remain in that condition just by itself. Because that's passive stabilization, right? That is just you put it in spin, and it will more or less remain in that condition without you having to use propellant or power or anything else. It will stay there by itself. That's great. You want to use this kind of properties. Okay, so that's the kind of equation that I'm going to write, actually, that ddt of h bar in n is equal to 0. Before I do that, let's just define quickly, and I'm sure you guys in controls classes have seen this in a more formal way. But stability of a system, I'm going to do a quick definition. A system is stable if, when perturbed, what am I writing? What am I writing here? Perturbation. Okay. Its motion remains in the vicinity of the unperturbed motion or trajectory within a, what do we call it, an amplitude of the same order of the perturbation. Does it make sense? You can say no. So if I think about these in terms of a three-dimensional trajectory, for example, system is stable if when perturbed its motion remains in the vicinity of the unperturbed motion within an amplitude of the same order of the perturbation. So say that your unperturbed motion for a particle, for example, is this given trajectory. This is the nominal trajectory without perturbations. This is what your particle will do. And then at some point in time, you add a perturbation of a given magnitude. So if this is an actual XYZ trajectory, you can quantify the magnitude as the norm of this vector that you're adding. You just give it a kick and push it sideways. So your trajectory now is going to go away to this point and will do something else. Now, if you remain within a tube, if you like, that has a radius which is of the same order of the initial perturbation, then you're stable. Does it make sense? And this is not only in X, Y, Z. This could be an n-dimensional state where n-dimensional space where your state vector is multiple variables, some are positions, some are angles. It still applies. So you have a nominal trajectory. You're going on the road. Everything is fine. Then at some point, the wind pushes you away. You kind of still stay on the road. You don't go off-road. That's the idea. And this is simple stability. You remain in here and you oscillate. You can actually touch the sides of the tube and remain there. As long as you remain there, you don't diverge. You're stable. Then there is the concept of asymptotical stability, and I'm sure you know what that means. It's an additional benefit that not only you remain in the vicinity of the motion, you actually, with time, converge back to the unperturbed motion, right? So let me just write it here. Converges to nominal motion after a perturbation. Now, many of you are in controls classes. Perturbation. I'm having a hard time with this word. I don't know why. You don't like perturbations. So this is just blah, blah, blah definition. There are mathematical definitions which I don't really need to go into it. But the one thing I need here is the following. If I have a linear time invariant system, which we usually write the following way: x dot equals ax. How many have seen this state space representation? This class is not going to be in your test, okay? I'm just showing you how some of the things we've seen are applied. So I'm collecting things together from different other classes. We just need them. So this x is a state vector. So again, it can be a bunch of different variables. It can be a vector of 12 components, like it would be for a spacecraft. Sometimes it's 13. Position of center of mass, its velocity, 3 Euler angles, angular velocity. So everything can be there. And this is linear because this is a constant matrix, and it's not changing with time. So that's why it's called a linear time invariant system. So if you have a linear time invariant system, the system is stable when? Remember when? There is a property for A.
When the eigenvalues of the matrix A
Eigenvalues are the real part. Skip an important piece here. Real part of eigenvalues of A is less or equal to 0. If you have some zeros, they can't be multiple roots. You want to have one zero. If you have two zeros, you're in trouble. But then it is also asymptotically stable. Yes, if it's the same real part of eigenvalues are strictly negative. That's asymptotical stability. You have the damping factor. You will kill the oscillations and will go back to the nominal motion. For a system like this, the first means that it doesn't matter where you start. At the most, you oscillate. You don't amplify the oscillation. If you actually have less than 0 real part of the eigenvalues, you go to 0. Okay. So with this information in mind, I am going to do things that we are comfortable with, which is I'm going to manipulate a little bit my second Euler's law, and I'm going to say that I have a rigid body, of which I know a principal axis of inertia coordinate system, and I'm writing that law in the body axis, in the reference frame of the spacecraft. So d dt in n of h bar n, we said this is equal to 0, and we justified why we care about this. H bar in n is the tensor of inertia. So if I have a principal axis coordinate system is ixx bar ex circle cross ex plus I bar yy ey circle cross ey plus I zz bar ez circle cross ez, and this is going to be applied to my angular velocity, which is in the body frame is going to be omega x ex plus omega y ey plus omega z ez. And I'm not even trying to move on without just calling these ix, iy, and iz, just to make my life a little easier. So only terms that really survive are those that have the common unit vectors. So your final h bar projected in the coordinate system, which is fixed to the body, is ix omega x little ex plus iy omega y little ey plus iz omega z little ez, which is beautiful. This is a very nice vector. If I didn't have a principal axis of inertia coordinate system, I will have all the products of inertia. This vector will be much, much bigger to write. Now, look at this. In which type of coordinate system am I expressing this vector? What is it? It's in the body. It's projected in the body. So that's not the inertial one, but I want the rate of change in the inertial one. So what do? I need to compute that ddt. Right? No surprise. So you take this vector, you do its rate of change with respect to the body, which I called r, right? Of h bar in n, plus you have to add the angular velocity cross with h itself, right? Why am I doing this? Because I'm able to write h bar in this way. It's easier. And then I have to do this operation. So, well, shouldn't be too difficult. What do you get for the first one? What are the things that depend on time here if I am sitting, that I see changing if I'm sitting attached to the body? Only the omegas. So this is ix omega x dot ex plus iy omega y dot ey plus iz omega z dot ez plus, well, omega is still the same, omega x ex plus omega y ey plus omega z ez, which is crossing the same. Plus omega y. Okay, I am not going to do it. I'll just give you the final result here because I know that you guys are able to do cross products, right? So I'm just writing the second law of Euler in a body fixed coordinate system. The final equation is, just because I don't want to mess up the order here, you get three equations, of course. Once you project it on the axis, you get ix omega x dot minus iz minus iy omega y omega z equals to 0. We said there is no moments. or the only, in other words, the only forces applied to the center of mass, Ix minus Iz omega z omega x equals 0. And the last one, omega y omega x equals 0. Okay. These are also called Euler's equations. For a rigid body, this is the second law of Euler with no moments projected in the body coordinate system. Okay. Is it clear how I get here? You don't need me to do all the cross products, right? I basically do the cross product that is left here, and then I start writing everything that multiplies little ex. That's the first, then ey, and then ez.
So it's equal to 0 because we have no moment.
We have no moment because I said all forces, if there are any, are applied to the center of mass. It's an approximation. If you have a huge spacecraft like the International Space Station that extends especially radially, the force of gravity does change. And so the center of mass is not where you would assume that the center of mass is not where you assume the force of gravity to be applied to exactly. But you can make that assumption when the spacecraft is not that big. Now, my nominal motion, remember, because I want to study the stability now of this. Nominal motion is omega Rn equals to some omega y. Remember, this is supposed to be a constant. What do we want to call this? If I do this, it looks like center of mass. Yeah. How about omega y 0? I'm sorry? Do you have another better? Yeah, omega y star. Yeah, why not? I like that. So this is assumed to be my constant spin rate times Ey, right? This is what I would like to see all the time. But say that I have a perturbation, I have to study how the system responds to a perturbation. So the perturbed motion, I'm going to say that it's some omega Rn, which now has an omega x on Ex plus an omega y star plus a perturbed omega y, which I'm going to call omega y 0, so I can use that as well, Ey, and then omega z E z. And I need to make some assumptions here. I'm going to say that omega x, omega y 0, omega z, and then also the rates in time are much smaller than omega y star. So there are small perturbations. Okay? So this is what I would like to see all the time, but something hits my spacecraft and triggers some small angular velocities on the axis where I would not like to see them, and I want to see what happens to those equations. Does it make sense? So now what happens if I start substituting the new omega in those equations and neglecting the second order term or the high order terms? Well, I see an Ix omega x dot minus Iz minus Iy. So I have omega y times omega z. So I have to multiply these two components. And I can do it here if you like. I see an omega y star plus omega y 0 that is going to multiply this omega z, right? What survives? Which of the two survives? The left one. This is the one I want to keep. This is a higher order than this. It's, in other words, it's actually much, much smaller than this, because this is multiplying two of the perturbations, which I said are much smaller than omega y star. So I only keep omega y star omega z. Do you agree? Okay. The second equation is I y omega y dot minus I x minus I z. Now multiplying directly omega z and omega x, these times these, I said those are small perturbations, so it's already a second order term, so this is basically going to 0. Am I making sense? I want to see if I've done it with the y-axis here. Have I done it with the y-axis? Yeah. Okay. Okay, so that's my second equation. Of course, this is linearizing them, right? It's not exactly what is going on, but I'm neglecting the smaller terms. Yz omega z dot minus Iy minus Ix. And now again, I multiply omega y times omega x. And as I've seen before, the only terms that survives is this omega y star, which is multiplying omega x equals 0. So these are my approximated equations of motion after a perturbation. Remember, the omega y star is something you create as your initial spin. It's usually pretty high speed. So it's much bigger than the perturbation, hopefully. Of course, there is a limit. If you give it a very high perturbation, we may not be able to use this approximation. So I start studying here. What I would like to see is that the omega y does not go away from this too much, and the omega x and omega z also remain close to 0, because they were 0. I would love them to remain 0, but unfortunately I have a perturbation. I have probably to have to live with that, but I want to see if it diverges, if it actually is going to increase. So let's look at this system. What can you tell me about stability? First of all, this is not a no-linear system anymore. This is a constant, this is a constant. This is really looking like a linear system. And all these i's are constants, so this is going to look like a LTI. So I can use what I've just told you about eigenvalues. Why would I have bothered doing that otherwise? Okay, but the second one, I can just look at it by itself. So it's completely independent from the other two, right?
Yeah.
Is this stable?
That gives you 0.
So is omega y changing? No. So it is stable. Does it make sense? So in other words, my new omega on the y-axis, yes, it is this omega y bar plus whatever I added, but it's not going to increase or decrease. It's just going to stay there because the omega y dot is 0. Am I making sense? So it's not going to converge back to this number. It's going to keep this additional omega y naught, whatever that is, but it's not exploding with time. It's staying there. So this is stable. Not asymptotically stable, but it's stable. And that's good. And then, okay, that's one. Then the other two, I'm going to do the following. I define my state vector to be, guess what? Omega x, omega z. And rewrite those equations the following way. I see omega x dot omega z dot. So this will be my x dot vector, which is multiplying some matrix that I need to populate here times omega x omega z, which is my vector capital X. So this would be my A, which I need to study. I need to find its eigenvalues to see if these are the two equations which are coupled are give me a system which is stable. So the other two will tell me if also the component of the angular velocity on x and z is going to stay limited or is going to explode. Hopefully not. Okay, so what do you put in here? If this is omega x dot, I bring everything on the other side, I only see a term here. I have a 0 here, and then I have this I z minus I y divided by ix, which is multiplying this constant angular velocity omega y star. Cool. And then this last one.
You mean to put on top?
Oh, I'm sorry. Yeah, that needs to go on top. Yeah. Thank you. I do matrices in diagonal, which I shouldn't do. Yeah. So omega z dot, bring everything else on the right-hand side. I don't see anything with the z, so here I have 0, and here I have something similar, iy minus ix divided by iz, which is multiplying y, omega y star. I have my A. I need to find the eigenvalues. How do you find the eigenvalues of a matrix? Characteristic equation. Does it sound familiar? Determinant of what?
A minus I lambda.
Lambda I, which in this case turns out to be, yeah, basically you have to find the determinant of minus lambda iz minus iy over ix omega y star, and then here I have, well, I have another minus lambda here, iy minus ix over iz omega y star. I have to set this to be 0. If I can make those eigenvalues look like I want, I may be lucky, and the other two angular velocities also stay within the perturbation. So what is the determinant of that is a lambda squared minus that, so equals the product of the two, right? If I set it to be equal to 0, right? Okay, so I get an omega y squared, and then I have, down here I have I, z, I, x. Numerator is I, z minus I, y, I, y minus I, x. Okay, so if you take the square root of this, I get plus minus, this was a squared, of course, so it goes away, square root of this. I'm going too fast? No? Good? Okay. What do you want this to be?
Well, you get a pair of complex conjugates of line.
That's the only you can have, right? That's the only thing you can have.
Stable, non-asymptotically.
It's not going to be asymptotically stable. There is no real part you can get out of this. If you allow this to be a real number, you're going to have a plus. You're going to have a positive eigenvalue, which is bad. So the only hope you have if this under the square root is a negative number, so that this comes out to be a complex number. So you have oscillations, but at least it's a simply stable system. Making sense? For those who are taking controls, yes. But believe me, that's what you want. So in other words, you have case 1 where iz minus iy is, for example, negative, and iy minus ix is positive. That's one case. Case 2, you also don't want the zeros. If you have 0 in any of these, is any of these moments of inertia are equal, you get 2 zeros, which is bad as well, right? So you want to be these different from each other. And then the other case would be iz minus iy is now positive, and iy minus ix is now negative. And so the final observation of this is what I gave you last time, anticipated last time, and now we have demonstrated this, is that your spin motion is stable if the spin axis, which remember was the y-axis, is either the axis of minimum inertia, which is case 2, right? Or maximum inertia, which is case 1. So when you design your spacecraft and you say that you want to spin it and put a sensor on that axis, you better pick one of the two. Otherwise, if you pick the intermediate inertia axis, which in this example, I don't know which one it is, it depends on how you pick IZ and IX, it will not remain there. If you spin it about the axis of intermediate inertia, the motion will do some strange things and it will eventually converge to one of the other two, in principle. This is what rigid body mechanics tells us, but the truth is that this is also not a good one. Because, as I mentioned to you, I sent you the links a few days back. In 1958, the US launched the Explorer 1, which was designed to spin about the axis of minimum inertia. It looks like a rocket. It's a spacecraft, but it really looks like a pencil, a rocket. So it was designed to spin about this axis. They put it into orbit, started the spin about this axis. A little bit later, the motion was not maintained, and he ended up spinning about the axis of maximum inertia. Because this is still an approximation, and not just the fact that I've linearized the equations. Here I don't have any flexibility. I'm assuming that everything is rigid. There is no dissipation of energy, which is not true. So after 200 years after Euler came up with his laws, people had to come back and revise a little bit of dynamics, rotational dynamics, and figure out why this would not hold while this was working. And we're not going to do it, of course. The class is almost over. But introducing the idea of flexibility and dissipation of energy, you can show that this is not stable. So you actually have only one choice. But it's good, because this is natural motion. You start a spin, and in principle, you will stay there. So any questions on this? This is just to show you that what we've done is actually being used and is still used for spacecraft, for example. But dynamics is not a static topic, it's a dynamic topic. So people keep finding out things, even experimentally, like in this case. So I'm going to leave you with the following. If you have an interest in spacecraft in general during your graduate school, we have some classes, of course, in this department. I think I'm going to introduce a new one in a year from now, in spring 16, about spacecraft attitude, determination, and control. But there is definitely one on dynamics. So this is really scratching the surface. There is a lot more you can do with the equation, Euler's equations, and the dynamics of a spacecraft as a rigid body. So it's fun stuff. If you have an interest, let me know, because I'll be offering this as a graduate class. We're not going to have a lecture on Wednesday. So I just wanted to tell you thank you for the opportunity of teaching my first class to you guys. It's been a pleasure. I had fun. This was my first Edge class. I'll give you the test tomorrow evening. Tomorrow? Yes. And give you 24 plus hours to do it, as last time. If you have any questions before the test, let me know. During test, no, unless I made a mistake in the test, which is that obvious. Hopefully not. During your graduate studies, of course, keep in touch. If you need anything, I'll be always available. And I'm not that good at preparing speeches for the last lecture, but what worked for me is just put your health and education at the top of the list, and you'll be happy. That's I think, the only advice I can give you. So good luck with everything. Thanks again.